Hello, and welcome to this film, which is all about writing and balancing chemical equations. Now, it might seem slightly odd to you that this is in the middle of a series of films about quantitative chemistry where we deal in calculations, but hopefully by the end of this film it will be obvious why it's here, and hopefully you'll understand the law of conservation of mass, that things can't be created or destroyed, and therefore equations have to be balanced. You'll know which numbers we can and can't change when we're trying to balance an equation, and you'll be able to look at the coefficients, what we call the coefficients in a balanced equation, and relate that to a mole ratio in a reaction. Okay, so let's start off quite simply by turning some words into symbols and writing a balanced equation. I'm going to be fairly quick with all this because I assume that you've done a fair bit of balancing equations before. And that you've learned your ion list so you can work out the formulas of things. If you still haven't done that by now, I would suggest you get onto that urgently. Anyway, water reacts with sodium to produce sodium hydroxide and hydrogen. So the formula of water is H2O. It's reacting with sodium, which is an element which hangs around on its own. It's not diatomic, so that's the formula of sodium. Produces sodium hydroxide, which I should be able to figure out from the charges on the ions, is NaOH. And hydrogen. H2. Hydrogen is an element which does hang around in pairs. Can't just write H for it. Okay, now balancing an equation, as I hope you realise already, is about changing the coefficients, or these numbers that go before the things in an equation. I can't just go fiddling around with these subscripts and changing the formulas of substances. That's playing this kind of chemistry god and deciding that, oh, okay, I don't want hydrogen to have that formula anymore. I'm creating this new form of hydrogen. Okay, so I'm not allowed to change those. All I'm allowed to do is change the big numbers. Okay, now I've got 3 hydrogens here. I've got 2 here, so any multiple of this is going to give me an even number. So let's just put a 2 here. So I've got 4 here altogether, and then I'll multiply that by 2. That's balanced the hydrogens, and I can see also that I've got 2 oxygens here and 2 oxygens there. The only thing that isn't balanced here is the sodium atom, so I'm going to put a 2 there as well. And I've changed the stoichiometric coefficients in the equation. I haven't changed anything else. Why have I done this? Because atoms can't just mysteriously appear or disappear. That's the law of the conservation of mass. Okay, matter can't be created or destroyed in a chemical reaction. You can just, atoms can be rearranged, but not created or destroyed. Okay, so that's our first equation. As you've probably seen there, we had to know formulas even to be able to make a start on it. So again here, I need to know the formula of methane, that's CH4. Okay, it reacts with oxygen, and I need to remember that's a diatomic element. Okay, it's forming carbon dioxide and water. Right, so here's an element. Here's a compound that had carbon and hydrogen in. We burn it, and it forms carbon dioxide and water, just like in our combustion analysis. Okay, now this time I've got 4 hydrogens here and 2 there, so I'm going to put 2 there. I've now got 4 oxygens over here, so I'll have 2 oxygen molecules here. That will give me 4 oxygen atoms, and I've got 1 carbon there and 1 carbon there. Again, I haven't fiddled with any of the numbers except for those that go before the substances. They are the stoichiometric coefficients. Now, why am I making such a big deal about these stoichiometric coefficients? I mean, most of us probably know about balancing by now, so what's the big deal about them? Well, the really important thing about a balanced chemical equation is that it allows us to find a mole ratio. So this balanced chemical equation, which tells me that I've got 1 nitrogen and 3 hydrogens reacting together to form 2 ammonia molecules, this tells me that for every 1 mole of nitrogen, I would need 3 moles of hydrogen to react with it, and I'd produce 2 moles of ammonia. And on that basis, I should be able to use that mole ratio to figure out the answers to questions like these. So, for example, how many moles of hydrogen do I need to react with half a mole of nitrogen? Well, if the number of moles of nitrogen is 1, and the number of moles of hydrogen is 3, then the number of moles of nitrogen is 1/3 of the number of moles of hydrogen. I can write that. In fact, it's useful if I can write that kind of thing. as a mathematical expression. The number of moles of nitrogen is a third of the number of moles of hydrogen. In other words, the number of moles of hydrogen is 3 times the number of moles of nitrogen. Okay, and if I know that, then I can easily find the number of moles of hydrogen. It's just 3 times 0.5, so that's 1.5 moles. Okay. What is the most ammonia that I could produce if I had 150 moles of nitrogen? Well, the number of moles of ammonia is 2. The number of moles of nitrogen in this balance equation is 1. So the number of moles of ammonia is twice as big as the number of moles of nitrogen. So if I could get all these 150 moles of nitrogen to react to produce ammonia, then I'd have twice as many moles of ammonia, so that would be 300 moles. How many moles of ammonia will form if I have 0.6 moles of hydrogen? Well, this is leading us on to a slightly more interesting question, I think, which is about what is the limiting reagent in this reaction? And that's something that we're going to look at in a bit more detail in an up-and-coming film. But you could say that just because I've got 0.6 moles of hydrogen, it doesn't mean I'm going to have enough nitrogen to react with it. Okay? So I can't be certain about how much ammonia is going to form. But if assuming I've got enough nitrogen to react with all my hydrogen, then I can predict how much ammonia will form. Now the number of moles of ammonia, which is 2, that is 2/3 of the number of moles of hydrogen, because the number of moles of hydrogen is 3. And again, it's very useful if you can write down these kind of algebraic relationships using the mole ratio in the equation, because it makes your working very much clearer for the examiner to mark. Okay, I've got 0.6 moles of hydrogen, 2/3 of that is 0.4 moles. Okay, so really and truly, I suppose, in this film, we didn't spend a great deal of time explaining how to balance equations. I'm kind of assuming that as prior knowledge. But we have talked about the law of conservation of mass, the reason why equations have to be balanced so that atoms aren't just appearing or disappearing. And what we've also done is we've linked what we're talking about here to mole calculations. And this ability to get a mole ratio from a balanced equation is going to be absolutely crucial in the upcoming films about calculations. So if you've got any questions from this one, please make sure you ask them as soon as you can, either by coming to see me or by posting a comment on YouTube, and try and make sure you get some practice at these kind of problems.